Hello my friends and welcome back to the You Can Do TV channel. The Sunward multi-purpose rotary drilling rig is designed for creating cast-in-situ board piles, essential in constructing large-diameter piers and high-rise building foundations. The rig incorporates key components from top international brands, including the engine, hydraulic pump, motor, and hydraulic valve, ensuring high performance and reliability. Its unique retractable undercarriage, developed independently, provides superior stability compared to competitors using standard excavator chassis. The advanced control system, also independently developed, features high integration, multiple functionalities, quick responses, and high accuracy. This system allows the Kelly bar to be self-assembled and disassembled, enhancing operational efficiency. The rig's patented parallelogram system enables a larger drilling radius while maintaining stability. It supports various drilling tools, making it suitable for different geological conditions like clay, sand, pebble, and weathered rock. This versatility is ideal for constructing foundations for highways, railway overpasses, viaducts, and more. The Dhaka-Khulna, North-8, Road Improvement Project, officially titled Improvement of Jatrabari Intersection, including Akuria Babu Bazar Link Road, to Pachchar Banga through Mava Road of Dhaka-Khulna, N8, highway to 4-lane with separate lane for slow-moving vehicles project, represents a significant infrastructure initiative aimed at enhancing connectivity and transportation efficiency between Dhaka and Khulna. Executed by the Special Works Organization West, SWO West, of the Bangladesh Army and funded by the Government of Bangladesh, GOB, the project is supported by Max Rankin JV as the development partner. This comprehensive approach is designed to facilitate smoother traffic flow, reduce congestion, and improve safety on one of the country's vital road arteries. The project involves the construction of two major bridges, Daleswari Bridge 1 and Daleswari Bridge 2, along with the expansion of the highway into a 4-lane road with separate lanes for slow-moving vehicles. Daleswari Bridge 1 is a precast concrete (PC) girder bridge spanning 362.8 meters. The bridge's construction includes 190 piles, 14 piers, and 8 spans, with 64 T girders, each 43.3 meters long. Additionally, 9 pile caps and 3 float-in box shutters are used, with the girder lifting, shifting, and erection processes managed using a girder launcher to ensure precision and stability. The project also includes several general and site facilities, such as the maintenance of temporary and diversion roads to ensure continuous traffic flow during construction, alongside measures to protect traffic and ensure safety. Earthwork involves clearing and grubbing, roadway excavation in unsuitable soils and existing pavement, earth excavation, and embankment filling. Sand filling for structures and swamps, as well as the installation of preload, prefabricated vertical drains, PVD, filter geotextile, impervious geotextile, and subgrade drains, are critical steps for preparing the ground and ensuring a stable foundation for the new road and bridge structures. Pavement work includes repairing existing pavement, laying subbase, 11,853 cubic meters, aggregate base type 1, 12,926.71 cubic meters, and aggregate base type 2, 9,449.51 cubic meters. Dense bituminous surfacing for both base and wearing courses using bitumen grade 60/70ths and rigid pavement, C35, totaling 5,137.968 cubic meters are applied. These pavement layers are designed to withstand heavy traffic and environmental wear and tear, ensuring longevity and durability. Foundation work is fundamental to the project's stability, involving board cast in situ piles with a 1200 diameter, both in regular and waterlogged areas with cofferdam. The total concrete quantity, C30, for piling work is 60,201.937 cubic meters. Pile testing, including static load tests, 800 tons, pile dynamic analyzer load tests, 800 tons, and pile integrity tests, 1,122 NOs, ensures the robustness of the foundation to support large-scale infrastructure. Structural components include pile cap, pier, abutment, pier cap, and RCC wall concrete quantity, C30, totaling 40,589.696 cubic meters, with PC girders numbering 720 units and 21,600 RM, and deck slab concrete quantity, C41, totaling 4,963.652 cubic meters. The installation of expansion joints, pot bearings, and E-wall, 3,762.704 square meters, ensures the structural integrity and resilience of the bridge and roadway to handle future traffic demands. Daleswari Bridge 2 combines T-girder and box girder designs, stretching over 591.54 meters. It involves 244 piles, 18 piers, and 10 spans, with 48 T-girders, each 43.3 meters long, and 142 box segments with span lengths of 90 meters and 67.5 meters. This bridge is a critical component of the project, designed to support heavy loads and withstand the region's dynamic environmental conditions. These two bridges are integral to the project's goal of improving transportation infrastructure. Incidentals cover a wide range of additional works to enhance road functionality and aesthetics, including cement concrete blocks, RCC drains, gully pits, U-shaped cover drains, HDPE pipes, concrete curbs, New Jersey barriers, roadside guard rails, RCC rail and posts, road signage, lampposts, road markings, landscaping, road beautification, grass troughing, and glare barriers. Bus bay passenger shades and other amenities are also part of the project, with a total concrete quantity for incidental works, C30, C25, being 7,666.97 cubic meters. These elements contribute to the overall usability, safety, and visual appeal of the improved highway. The Dhaka-Khulna, North-8 Road Improvement Project is a landmark infrastructure development aimed at significantly enhancing transportation efficiency between Dhaka and Khulna. With robust planning, advanced engineering techniques, and comprehensive execution, the project promises to bring substantial economic benefits and improved quality of life for the region's inhabitants. The project's multifaceted approach ensures that the infrastructure will be resilient, safe, and capable of supporting the region's future transportation needs. Construction of slipform barrier for Sabanche Trans-Sumatra Toll Road. Land clearing. The construction site is prepared to ensure a smooth and stable foundation for the subsequent construction activities. A lean concrete layer, Hampar LC, is laid down. The lean concrete helps in reducing settlement and provides a solid foundation for the barrier. Iron settings. Next, the iron settings are arranged. The rebar structure is crucial for providing tensile strength to the concrete barrier. Install the conduit pipe. Conduit pipes are also installed as required. These pipes are embedded within the concrete to accommodate utilities or drainage requirements. Cast iron reinforcement. Once the rebar and conduit pipes are in place, the iron reinforcement is cast. This involves pouring concrete over the arranged rebar to encase it fully, creating a strong and cohesive structure. Slump test measurement. A slump test is conducted to measure the workability and consistency of the concrete. This test ensures that the concrete mix has the right properties for effective casting and curing. Finishing barriers. After the concrete is poured and shaped using the slipform method, finishing work is performed on the barriers. This includes smoothing and leveling the surface to achieve the desired texture and appearance. Make dilation, expansion joints. To accommodate thermal expansion and contraction, dilation, expansion joints are created at regular intervals. These joints prevent cracking by allowing the barrier to expand and contract with temperature changes, maintaining its structural integrity. Curing compound. To ensure proper curing of the concrete, a curing compound is applied. Results of barrier work. The final stage involves inspecting and evaluating the completed barrier work. The first step in the girder erection process is transporting the girder from the stockyard stressing location to the erection site. Girders that have been prepared and stressed in the stockyard need to be moved to the erection site using specialized transportation equipment. This equipment is capable of handling the heavy and long girders, ensuring their safe and secure arrival at the erection location. Once the girder arrives at the erection site, the next step is to attach the lift points to the crane. The lift points on the girder must be identified and prepared for connection to the crane. The sling is then attached to the girder's lift points, ensuring the attachment is strong and correctly positioned to maintain balance during the lifting process. This careful preparation is critical to prevent accidents and ensure the girder is lifted smoothly. Before the actual erection begins, it is essential to install body harnesses on the workers. Workers operating at high elevations are required to wear body harnesses to ensure their safety from fall risks during the erection process. These harnesses are a vital safety measure, providing security for the workers as they perform their tasks at significant heights. The erection process itself involves the crane lifting the girder slowly from a horizontal position on the ground to a vertical position. The girder is then lifted and positioned according to the design plan and the predetermined location. Workers on site ensure that the girder is in the correct position before it is permanently installed. This step requires precision and coordination to ensure the girder fits perfectly into its designated spot. After the girder is placed in its intended location, temporary bracing between girders is conducted. This temporary bracing is crucial for maintaining the stability of the girders and preventing any risk of tipping or shifting before the permanent fastening is completed. The braces act as a support system, ensuring that the girders remain in their correct positions during the entire erection process. Once the girder is securely installed and stabilized with temporary bracing, the final step is releasing the lift points from the crane. The lift points that were previously connected to the crane are carefully detached. Workers ensure that the girder's fastening is strong and stable before the crane hook is released. This final check is essential to confirm the girder's secure placement and to ensure the safety of the structure. Beam launching using girder structures is a critical process in bridge and infrastructure construction, where precision and safety are paramount. At Gamuda Gardens in Rawang, this method was employed to position massive 63-meter-long beams, weighing 114 tons. The girder launch method involves using a girder, essentially a large horizontal support beam, to facilitate the placement of the main beam into its designated position. In this case, the 63-meter beam was carefully aligned and lifted using specialized lifting equipment. The girder served as a stable platform, ensuring that the beam was securely supported throughout the process. Key steps in this operation included precise alignment and stabilization of the girder. Engineers ensured that the girder was robust enough to bear the beam's immense weight and that it was properly anchored to prevent any movement during the launch. Hydraulic jacks and cranes were employed to lift the beam onto the girder, which then guided it into place. Safety measures were rigorously followed to mitigate any risks associated with the beam's substantial weight and length. This included thorough inspections of the equipment, continuous monitoring of the beam's alignment, and coordination among the engineering and construction teams to manage any unforeseen challenges. The successful beam launching at Gamuda Gardens showcases the effectiveness of using girder structures in modern construction projects. This method not only enhances the precision and safety of beam placement but also demonstrates the engineering prowess required to handle such large-scale infrastructure components efficiently. The following animation demonstrates how asphalt is laid using compact asphalt paver and feeder. First, the feeder machine fills the binder hopper, indicated in green. Then, the feeder repositions itself to transport the wearing coarse material to the upper hopper on the paver, filling it with the material colored red. Now, the top two asphalt layers can be laid in a single, continuous process, hot on hot. Let's take a closer look at the construction of the compact asphalt machine. We see the first module, a binder container expanded to 45 tons, connected to the carrying basic unit, the F300CS paver. This binder container is self-supporting in design. Next, the paver connects to the second module, the AM300, which includes a 25-ton storage container for the wearing coarse material, 2 feeder augers, a chute, and a second screed. To attach the AM300, the paver backs into the module and locks it in place. The compact asphalt design facilitates easy transportation from one site to another. Let's see the compact asphalt system in action alongside the mobile feeder, the MF300C, on a country road in northern Germany. The working width is 6 meters. Binder material, 0-22s, with a thickness of 10 centimeters, and wearing coarse material, SMA 0-11S, with a thickness of 2 centimeters, both using polymer-modified bitumen, are processed. The green light on the mobile feeder indicates the need for binder material in the larger binder container, reflecting the binder layer's thickness. A lorry delivers binder material, which the feeder's conveyor belt transports to the compact asphalt binder container. The Dynapac feeder can load 27 tons of material into a paver hopper in just 35 seconds, ensuring continuous paving. The binder material is laid with the first high compaction screed, using proven serial components. Once the binder hopper is filled, the feeder raises its conveyor to fill the upper container with wearing coarse material. The hopper augers distribute the wearing coarse mix to the second screed, where it is pre-compacted on the hot binder layer, ensuring optimal interlocking and bonding of the layers. This method, hot on hot, contrasts with conventional methods where the wearing course is paved on a cold base layer, enhancing compacting time for subsequent rolling. Roads constructed with the compact asphalt method meet modern transport demands with extreme wearing stability and smooth surfaces. Compact asphalt can be laid even in cooler months due to the residual heat in the binder. Using a 10 cm binder and a 2 cm wearing course extends compaction time significantly, allowing for efficient work even with substantial temperature loss. Initial compaction is done by small rollers in static mode to stabilize the layer's thickness before vibratory compaction. Heavier vibratory rollers follow to achieve the required compaction, and stone chippings are rolled into the surface for initial friction. The advantages of this process include high-quality, deformation-resistant roads completed in a short time. Here are some impressions from various worksites and surfaces after compaction. The main benefits of compact asphalt technology are its longer life cycle, modular units attachable to standard pavers, shorter construction time, higher quality, and increased economic efficiency. Conveyored road cloth placement technology, CRCPT, is an innovative method used for placing geosynthetic cloth in road construction projects. This technology utilizes conveyor systems mounted on trucks to efficiently and accurately lay down geosynthetic materials, which are crucial for reinforcing and stabilizing soil structures in roadbeds. By automating the placement process, CRCPT significantly enhances the speed and precision of installation, reducing manual labor and minimizing human error. This results in a more consistent and reliable application, crucial for the longevity and durability of the road. Additionally, CRCPT improves safety conditions by limiting the need for workers to be in potentially hazardous environments. The use of this technology leads to more efficient project timelines and can lower overall construction costs, making it an advantageous choice for large-scale infrastructure projects that require extensive use of geosynthetic materials. The construction process for the rigid pavement on the Sigli Banda Aceh toll road involves several systematic steps to ensure durability and strength. The process begins at the batching plant, where raw materials are mixed to create Beton FS45 concrete. Once prepared, the concrete is loaded into trucks for transport to the construction site, ensuring it remains workable during transportation. Upon arrival, a slump test is conducted to measure the concrete's consistency, with a target slump of 3 to 4.5 centimeters, confirming the mix meets the required specifications. Next, the concrete is evenly spread across the prepared subbase using machinery, ensuring a uniform layer vital for the pavement's structural integrity. The finishing process follows, involving several steps to ensure durability and surface quality. Effective site coordination is crucial for the smooth execution of the pavement construction. This involves organizing materials, machinery, and workforce to ensure timely progress and quality control, preventing unnecessary delays. Rigid pavement, also known as concrete pavement, is constructed using aggregate materials bound together with cement, resulting in high rigidity compared to flexible pavements like asphalt. Grooving is performed first, creating grooves in the concrete surface to enhance traction and reduce skidding risk. A curing compound is then applied to prevent the concrete from losing moisture too quickly, essential for proper hydration and strength development. The surface is covered with geotextile fabric to retain moisture and protect the concrete during the initial curing period. Water curing is employed to maintain the concrete's moisture content, crucial for the curing process and achieving the desired strength. This step significantly impacts the pavement's longevity and performance. Once the concrete has gained sufficient strength, It is cut to a depth of 7.5 centimeters to create joints that help control cracking due to temperature changes and loading. These joints are then filled with a sealant to prevent water and debris from entering and causing damage. Ensuring cuts are to the specified depth, monitoring the temperature during sealing for proper adhesion and curing, and cleaning the area around the joints are essential for the sealant's effective application. A diaphragm wall is a structural element used in construction to provide strong and waterproof barriers in deep excavations, often serving as retaining walls, foundation walls, or cutoff walls. The technique is prevalent in urban environments where space constraints demand precise and efficient methods. Typically, diaphragm walls are composed of reinforced concrete and are particularly beneficial in projects requiring deep excavation and stabilization of the surrounding soil. Installation of diaphragm walls. The installation process of diaphragm walls involves several meticulously planned steps to ensure the structural integrity and functionality of the wall. In the context of installing 55 panels between 15 meters and 20 meters deep with a 600 millimeters wall thickness, the process can be outlined as follows. Site preparation. Before the installation begins, the site must be thoroughly prepared. This involves surveying the area, removing any obstacles, and setting up guide walls. Guide walls, typically shallow concrete structures, help maintain the correct alignment and width of the trench to be excavated. Trench excavation. The trench for each panel is excavated using a specialized clamshell grab or a hydraulic cutter. Excavation is conducted in stages to the required depth, with bentonite slurry used to support the trench walls and prevent collapse. Bentonite, a type of clay, forms a thixotropic fluid that stabilizes the trench walls by providing a counter pressure. Panel construction. Diaphragm walls are constructed in panels. For the 55 panels in question, each panel would be excavated and constructed sequentially. The dimensions, 15 meters to 20 meters deep and 600 millimeters thick, indicate substantial panels requiring careful engineering to ensure verticality and alignment. Excavation for each panel is conducted to its full depth before proceeding to the next stage. Reinforcement placement. Once the trench for a panel is excavated, a steel reinforcement cage is lowered into the trench. These cages are prefabricated according to the design specifications, ensuring the diaphragm wall can withstand the intended loads. The reinforcement cage must be correctly positioned and securely held in place. Concreting. Concrete is poured into the trench using the Tremie method, which involves placing concrete through a vertical pipe to avoid segregation and ensure consistent quality. The bentonite slurry is displaced as the concrete fills the trench, being recirculated and reused for subsequent panels. The quality of the concrete and the pouring process are critical, as any defects could compromise the wall's structural integrity. Installation of anchors. For diaphragm walls requiring additional lateral support, anchors are installed to enhance stability. The installation of anchors for approximately 60 linear meters of wall involves the following steps. Drilling anchor holes. Holes are drilled at specified locations along the diaphragm wall. The depth and angle of these holes depend on the design requirements and the characteristics of the surrounding soil and rock. Inserting and grouting anchors. Steel anchors are inserted into the drilled holes. Once positioned, the anchors are grouted in place using high-strength grout. This process ensures the anchors are firmly embedded, transferring the load from the wall to the surrounding soil or rock. Tensioning the anchors. After the grout has cured, the anchors are tensioned to the required specifications. This process involves applying a predetermined load to the anchors, ensuring they provide the necessary support to the diaphragm wall. GIPO Kombi RC130 FDR is a mobile track-mounted crushing and screening plant designed for recycling concrete and asphalt materials. It is a versatile machine that can be used in various applications, such as construction waste recycling, demolition waste recycling, and quarrying. The plant is equipped with a primary impact crusher, a secondary impact crusher, and a double-deck screen. The primary impact crusher has a capacity of up to 400 tons per hour and can handle large pieces of concrete and asphalt. The secondary impact crusher can produce up to 200 tons per hour and is ideal for producing a more refined product. The double-deck screen can be used to separate the different sizes of the crushed materials, ensuring that the final product is of the desired size and quality. It is also equipped with a magnetic separator, which is used to remove any metal contaminants from the crushed material. This is important because metal can cause damage to downstream processing equipment or even create a safety hazard if not removed. One of the key features of the machine is its mobility. It can be easily transported from one site to another, making it ideal for use in different locations. The machine is also designed to be easy to operate, with intuitive controls and a user-friendly interface. In terms of environmental sustainability, the machine is designed to minimize its impact on the environment. It is equipped with a dust suppression system, which reduces the amount of dust generated during the crushing and screening process. The machine is also designed to be energy efficient, with low fuel consumption and emissions. The Lorem Ballast Cleaner is a specialized machine used for cleaning and maintaining the ballast bed of railway tracks. The 1915 Canakkale Bridge, Turkish, 1915 Canakkale Köprüsü, stands as a monumental feat of engineering and a symbol of historical and contemporary significance for Turkey. Spanning the Dardanelles Strait in northwestern Turkey, the bridge connects the European and Asian continents just south of the coastal towns of Lapseki and Gelibolu. Officially opened on March 18, 2022, by President Recep Tayyip Erdogan, the bridge honors the Ottoman naval victory of March 18, 1915, during World War I, a pivotal moment in Turkish history. Design and engineering marvel. The 1915 Canakkale Bridge boasts a main span of 2,023 meters, making it the longest suspension bridge in the world, surpassing Japan's Akashi Kaikyo Bridge by 32 meters. The bridge's total length, including its approach viaducts, is 4,608 meters, making it the longest bridge in Turkey by total length. The bridge's towers rise to a height of 334 meters, making them the tallest in Turkey and the second tallest globally, surpassed only by the Pingtang Bridge in China. Designed by Techfen Construction and Installation with detailed designs from COWIAS and PEC, the project also saw the involvement of Arup and Oz Jacobson as independent design verifiers. The collaborative effort ensured that the bridge could withstand high winds, seismic activity, and accommodate high-stacked container ships. The bridge's deck, measuring 72.8 meters in height and 45.06 meters in width, supports 6 lanes of motorway traffic along with walkways for maintenance. Construction and financial aspects. The construction of the 1915 Canakkale Bridge was a major international endeavor involving a consortium of Turkish companies Limak Holding and Yapı Merkezi, and South Korean companies DL Holdings and SK Ecoplant. The project, which began in March 2017, was initially slated for completion in September 2023 but was completed ahead of schedule in March 2022. Financially, the bridge was a significant investment, costing approximately 2.5 billion euros, 2.7 billion US dollars. This investment is expected to yield substantial economic benefits, with anticipated annual savings of 415 million euros, 458 million US dollars, due to reduced fuel consumption and lower carbon emissions. Historical and symbolic significance. The bridge is imbued with symbolic references that celebrate Turkish history and national pride. The name, 1915, commemorates the Ottoman victory in the Gallipoli campaign, a critical event during World War I. The height of the bridge's main cable intersection point at 318 meters, and the opening date of March 18, further honor this victory. The main span of 2,023 meters also symbolizes the centennial of the Turkish Republic, which will be celebrated in 2023. Technological and construction highlights. The 1915 Canakkale Bridge's construction presented numerous challenges, including dealing with the region's high winds and seismic activity. Advanced engineering solutions were employed to address these issues, ensuring the bridge's stability and safety. The bridge's towers, which exceed the height of the Eiffel Tower without its antenna, were a significant engineering achievement. By November 2021, all block decks were installed, marking a critical milestone in the bridge's construction timeline. The project utilized the Build Operate Transfer (BOT) model, a common approach for large infrastructure projects where a private entity is granted a concession to finance, design, build, and operate the facility for a specified period. This model facilitated the involvement of 25 financial institutions from 10 countries, securing a 15-year term loan with a 5-year grace period. Approximately 70% of the financing came from foreign banks and financial institutions, with the remaining 30% provided by Turkish banks. Impact and legacy. The 1915 Canakkale Bridge is more than just an infrastructural milestone. It represents Turkey's aspirations and capabilities in modern engineering and international collaboration. The bridge significantly enhances connectivity between Europe and Asia, reducing travel time across the Dardanelles to just 6 minutes. This improved accessibility is expected to boost regional economic development and facilitate more efficient transportation of goods and people. Moreover, the bridge stands as a testament to Turkey's engineering prowess and its capacity to undertake and complete large-scale infrastructure projects. The bridge also serves as a poignant reminder of the nation's historical resilience and its forward-looking vision, bridging the past with the future. The Rail-Veyor technology is a unique transportation system that combines the best features of conveyors and rail systems. The Vale underground mine in Sudbury, Ontario, Canada, has implemented this technology to improve its mining operations. The Rail-Veyor system uses electric-powered, remotely operated trains that run on a track with a unique conveyor system. The trains can travel up to 25 miles per hour and can transport up to 300 tons of material at a time, making it a highly efficient method of transportation. At the Vale underground mine, the Rail-Veyor system has been used to transport ore from the mine to the surface. This has eliminated the need for trucks to haul the ore, which has reduced the amount of diesel fuel used and the associated greenhouse gas emissions. The Rail-Veyor system has also helped to reduce the number of accidents and injuries associated with traditional mining transportation methods. The Rail-Veyor technology has several other advantages over traditional mining transportation methods. It is quieter and less disruptive to the surrounding environment, as well as more cost-effective. The system requires less maintenance than traditional transportation methods and has a longer lifespan. Another benefit of the Rail-Veyor system is that it can be easily adapted to meet the changing needs of mining operations. The technology can be used to transport a variety of materials, including ore, waste rock, and equipment. It can also be used to transport materials over long distances and through difficult terrain. The production of T-wall concrete involves several critical steps to ensure high quality and durability. Here's an overview of the process: material and reinforcement preparation. The process begins with preparing the raw materials: high-quality Portland cement, fine and coarse aggregates, clean water, and necessary additives. Simultaneously, high-strength steel bars are cut and shaped into the required T configuration, which is essential for the structural integrity of T-wall concrete. Molding preparation. The process begins with preparing the molds. This involves thoroughly cleaning them to remove any debris and then applying a release agent, such as molding oil, to ensure the concrete does not stick to the molds during curing. This step is crucial for maintaining the integrity and ease of removing the final product. Applying molding oil. Next, the application of molding oil takes place. This oil acts as a barrier between the mold and the concrete, preventing the concrete from adhering to the mold surfaces. It also facilitates a smoother finish on the concrete surface and makes the demolding process more efficient. Placing reinforcement bars in the mold. The final step in the preparation phase involves setting the reinforcement bars into the molds. These high-strength steel bars, pre-shaped into the required T configuration, are carefully positioned within the molds according to the design specifications. Proper placement of these bars is essential to ensure the structural integrity and strength of the final T-wall concrete product. Concrete mixing. The measured materials are mixed in a concrete mixer. This precise batching ensures the concrete achieves the desired consistency and properties. The mixture is then poured into the molds, where the T-shaped reinforcements have been placed. Pouring and vibration. The concrete is carefully poured into the molds in layers to avoid air pockets. Each layer undergoes vibration using a vibro tool, which helps the concrete to fill all spaces within the mold and ensures a dense and solid structure. Curing. Curing is crucial for the concrete to achieve its optimal strength. Initially, the concrete sets in the molds. This is followed by a moist curing process, where the concrete is kept damp using water sprays or wet burlap to prevent premature drying and cracking. Demolding and finishing. Once the concrete has cured adequately, the molds are removed carefully to avoid damaging the concrete. The surfaces of the T-wall concrete are then finished according to project specifications, which may include smoothing or applying textures. Quality control and testing. Each T-wall unit undergoes inspection for defects and inconsistencies. Samples are tested for compressive strength and other properties to ensure they meet the required standards. Storage and delivery. The finished T-wall concrete units are stored safely to prevent damage and are then transported to the construction site as needed. A segmental launching gantry is an advanced piece of construction equipment primarily used in the erection of highway and MRT bridges utilizing precast segmental prestressed concrete box beams, PC beams. The HL-Kattor segmental launching gantries, known for their efficiency in self-traveling construction, consist of three main components: the main beam, legs, and winch trolley. Main beam. The main girder or beam is the principal load-bearing element. It supports the weight of the precast segments and other construction loads. Legs. The legs facilitate the transverse and longitudinal movements of the gantry, allowing it to position itself accurately along the bridge span. They provide support, leveling, and the ability to span across gaps. These legs are critical for moving the gantry from one segment to the next and maintaining stability throughout the construction process. Winch trolley. This component is responsible for lifting the precast segments into place. The trolley moves along the main beam, hoisting segments from below and positioning them precisely. Operational mechanism. Positioning. The gantry is moved into position using its legs, which can adjust for leveling and stability across varying terrains and slopes. Lifting. Precast segments are lifted using the winch trolley, which can handle substantial weights. The segments are brought up from below and aligned with the previously placed segments. Assembly. The segments are aligned and joined, often using methods such as full-span cantilever, symmetrical cantilever, or semi-span cantilever assembling, depending on the project requirements. Progression. Once a segment is in place, the gantry self-travels to the next position, continuing the process. This is HDD rig M8x12 on crawlers manufactured by Pride Engineering Company, Russia. The HDD M8x12 has a high lappet with chain transmission torque and tractive effort that allows you to plot a different kind of communication for a length of up to 300 meters. Drilling rigs equipped with diesel engine D442 and hydraulic system of European production. The rig has a rack and gear drive and automatic rod feed. Equipped with an operator's cabin, all necessary tool, tracking and mixing system by customer request. The Pride Production Company, Plant Pride, is a modern producer of special equipment. Its main advantage, an individual approach to solving problems of the client and the ability to manufacture equipment of any complexity. It is a reliable manufacturer of quality drilling rigs for vertical and horizontal drilling, mini loaders, mini excavators, and cleaving complexes and equipment for screwing piles. Statoil ASA is developing a new oil field in the North Sea. To transport the crude oil, a new pipeline is needed to the refinery. Part of this is the landfall to Statoil's refinery in Mongstad, Norway, which is made by means of a directional drilling (DD) through the extremely hard granite rocks. Visser and Smit Hanav has found a robust solution for this unique situation. The company's global specialists have designed a specific landfall to enable a 92 cm oil pipe to be pulled in from a pipelay vessel lying in the Fens Fjord, so that the pipe can be connected to the refinery. Designing and preparation lasted all summer, and after that working area was built up to start work. And the pilot drilling, 28 cm, was completed, and Visser and Smit Hanav's VNSH started the first dredging phase of 71 cm. The major challenges of this project are the varying rock formations and strata that make it difficult to predict the work and deploy the right strategy. Due to both the steep entry angle of 24.50 and the depth of the exit point at 315 meters below sea level, deviating measures had to be taken. Under normal circumstances, this 250-ton HDD rig operates with a maximum entry angle of 20 degrees. For the Mongstad project, VNSH designed and installed a steel frame construction to realize the required angle. The depth of the exit point poses even more interesting issue because of the pressure difference. At 315 meters below sea level, there is a great water pressure of approximately 31 bars. This pressure can push the seawater into the hole, causing the cuttings to flow back and clog the hole, causing the tools to jam. VNSH has also found a solution for this. Two huge seawater pipes have been installed with extensive piping to flush the cuttings out of the hole. Traditional clearing is not possible due to the water depth. Therefore, VNSH will enlarge the original hole by means of forward reaming in 3 steps. Diameters of 71, 97 and 122 centimeters. After this, the final installation of the 92 centimeters oil pipe can start. The first step in installing GRP pipes is to prepare the site and gather all necessary tools and equipment. This includes lifting slings, brushes, water-based lubricant, feeler gauge, coupling covers, separating devices, shovels, vibratory plate compactors, excavators, and pipe lasers. It's imperative to prioritize safety, ensuring that all personnel involved wear appropriate personal protective equipment such as gloves, hard hats, and protective footwear. Once the site is prepared and tools are ready, the next phase involves handling and storing the GRP pipes properly. Pipes should be loaded onto stable ground and, if necessary, placed on wooden supports to prevent damage during handling. Care must be taken to avoid any form of damage to the pipes, as even minor defects can compromise the integrity of the pipeline system. Certified lifting slings should be used for lifting operations to ensure safety and prevent accidents. Trench excavation is a crucial aspect of GRP pipe installation, as it sets the foundation for the pipeline. The trench must be excavated to the required depth and width, ensuring stability of the bottom to support the weight of the pipes. The use of a pipe laser can aid in achieving the correct trench depth and alignment, ensuring that the pipeline will be installed with precision. Once the trench is excavated, the next step is to prepare the bedding for the pipes. A stable bedding material, typically 100 to 150 millimeters thick, is provided to support the pipes and distribute the load evenly. Holes should be excavated where the couplings will rest to prevent the pipes from resting on the couplings, which could cause stress points and potential damage over time. With the trench prepared and the bedding in place, the pipes are ready to be joined together. Before joining, it's essential to clean the coupling grooves and rubber gasket rings to ensure a proper seal. Water-based lubricant is applied to the spigot ends of the pipes and the gaskets to facilitate smooth insertion and create a tight seal. A coupling cover is used during the joining process to prevent gravel or debris from entering the coupling, which could compromise the integrity of the joint. Alignment is crucial during pipe joining to ensure a seamless connection and prevent leaks. Pipes should be aligned accurately before pushing the spigot into the coupling, with care taken to avoid any misalignment that could lead to future issues. Once the pipes are aligned, they are pushed slowly and steadily into the coupling until fully inserted. Verification of gasket placement using a feeler gauge is essential to ensure a leak-tight seal, as any misalignment or improper seating of the gasket could result in leaks. After the pipes are joined, backfilling of the trench begins immediately to protect the installation and provide support to the pipeline. Native or imported soils are used for backfilling, avoiding organic or environmentally harmful materials that could degrade over time. Compaction of the soil is done in lifts of 100 to 300 millimeters using a vibratory plate compactor, ensuring proper support and preventing deformation of the pipes. Care must be taken not to overcompact the soil, as this could lead to stress on the pipes and potential damage. Throughout the installation process, attention to detail is paramount to ensure the integrity and longevity of the GRP pipeline. Proper handling, alignment, joining, and backfilling techniques are essential to creating a leak-tight and structurally sound pipeline system that will serve its intended purpose reliably for many years to come. By following these steps diligently and adhering to industry best practices, the installation of GRP pipes can be completed successfully, providing efficient and reliable infrastructure for various applications. The drinking water storage tank utilizing AmiBlue GRP, glass fiber reinforced plastic, prefabricated parts offers a cutting-edge solution for water storage needs. The Kreglingen project showcases a multi-chamber system featuring an intermediate slide chamber, providing efficient and versatile storage capabilities. With a nominal diameter of DN3000, this modular system allows for simple installation and later retrofitting, ensuring adaptability to evolving requirements. One of the standout features of this tank is its adherence to all drinking water standards, guaranteeing the safety and quality of stored water. The tight pipe connections further enhance its reliability, minimizing the risk of leaks or contamination. Additionally, the UV-resistant nature of the GRP material ensures long-lasting durability, even under harsh environmental conditions. GRP, composed of a polymer matrix reinforced with glass fibers, boasts exceptional strength and resilience. This composite material combines the compressive strength of plastic resins with the tensile strength of glass fibers, resulting in a robust and versatile product. Various production methods, such as filament winding and hand layup, allow for tailored designs to meet specific project requirements. The advantages of GRP extend beyond its mechanical properties. Its lightweight nature, coupled with high mechanical strength, makes it an ideal choice for a wide range of applications. Furthermore, its resistance to chemicals, corrosion, UV radiation, and temperature fluctuations ensures longevity and reliability in diverse environments. With its customizable features and long lifespan, GRP emerges as a sustainable and cost-effective solution for drinking water storage needs. The TerraTech microtunneling system, utilized in Bangkok's MRT Green Line North cable tunnel project, employs sophisticated engineering to efficiently excavate tunnels with precision and reliability. The TBM, boasting a diameter of 4.27 meters, operates on the principle of earth pressure balance, EPB, maintaining equilibrium between internal pressure and surrounding earth to prevent collapses. This TBM is specifically tailored for the South Bangkok Cable Tunnel project, aimed at meeting increased power demands and enhancing electricity distribution across Samut Prakan province. With a spoke-style cutter head featuring a 70% opening ratio, the TBM is well equipped to navigate various ground conditions encountered during tunneling, including silt, clay, and fine sand layers. To facilitate smooth excavation beneath the Chao Phraya River and alongside existing live HDD cable supply lines, the TBM operates in an alert mode, ensuring operational efficiency and safety. Geological considerations, such as a 35-meter average overburden and high groundwater pressure, necessitate specialized design features. The soft ground cutter head incorporates knife bits for enhanced penetration, while traditionally reinforced precast concrete segments provide structural integrity to the tunnel walls. Transportation of excavated material, segments, and machinery within the tunneling site is facilitated by a rail system, optimizing logistical operations. To cope with high groundwater pressure, an innovative non-tuck hose and belt conveyor system efficiently remove excavated material, tailored for Bangkok's sand stratum. Furthermore, the TBM's shield and backup systems are meticulously designed to navigate tight curves, with a turning radius of 40 meters. This ensures seamless progress around obstacles encountered during tunneling operations. In the contemporary context of emphasizing sustainability and effective management of urban sanitation and water supply networks, the adoption of the BIM, Building Information Modeling, methodology stands out as a crucial element. BIM modeling serves as a robust tool for supporting installation projects while efficiently managing and coordinating their designs. It ensures heightened productivity, time and cost savings, seamless conflict resolution, and meticulous representation of design nuances. According to insights from the public BIM Tender Observatory, the utilization of BIM methodology is mandated in over 70% of public tenders for new building construction in Spain. This underscores its pivotal role in shaping the management and planning processes of piping systems within such projects. The implementation of the Building Information Modeling (BIM) methodology for pipe systems installation offers numerous advantages that contribute to the efficiency, sustainability, and overall success of construction projects. Below are some key advantages of using BIM for pipe installation. Enhanced collaboration and coordination. BIM provides a centralized platform where all stakeholders involved in the project can collaborate in real time. This fosters better communication and coordination among architects, engineers, contractors, and subcontractors, leading to fewer conflicts and errors during the installation process. Early conflict detection. One of the most significant benefits of BIM is its ability to detect clashes or conflicts between different building components early in the design phase. For pipe systems, this means identifying clashes with structural elements, electrical conduits, or HVAC systems before construction begins, avoiding costly rework and delays. Optimized design and performance. BIM allows engineers to simulate and analyze different design scenarios for pipe systems, optimizing their layout, size, and routing for better performance and efficiency. This ensures that the final design meets the project requirements while minimizing material waste and unnecessary costs. Precise planning and scheduling. With BIM, project managers can create detailed schedules and plans for pipe installation, including sequencing and logistics. This enables better resource allocation, reduces downtime, and ensures that the installation process is completed on time and within budget. Accurate material orders. BIM provides detailed information about the dimensions, quantities, and specifications of pipe components, allowing for more accurate material orders. This helps to minimize waste and avoid overordering, leading to cost savings and improved sustainability. Asset management and maintenance. Beyond the construction phase, BIM models serve as valuable tools for asset management and maintenance throughout the building's lifecycle. Property owners can access detailed information about the pipe systems, including their location, specifications, and maintenance history, facilitating proactive maintenance and reducing lifecycle costs. Regulatory compliance. BIM models can help ensure compliance with local building codes, regulations, and standards related to pipe system installations. By continuously updating the model with the latest regulatory requirements, stakeholders can mitigate compliance risks and avoid costly penalties. Prefabrication and manufacturing assistance. BIM facilitates the creation of detailed models for pipe component manufacturing, enabling off-site prefabrication and assembly. This not only accelerates the installation process but also improves quality control and reduces on-site labor costs. Risk reduction and safety. By identifying potential hazards and safety risks during the design phase, BIM helps to improve overall safety on the construction site. Furthermore, by reducing conflicts and rework, BIM minimizes the likelihood of accidents and injuries during pipe installation. Sustainability. Ultimately, the use of BIM for pipe systems installation promotes sustainability by optimizing resource usage, reducing waste, and enhancing energy efficiency. By enabling more efficient design, construction, and maintenance practices, BIM contributes to the long-term sustainability of buildings and infrastructure projects. Underground blasting mining is a method of extracting minerals or ores from below the Earth's surface. It involves drilling boreholes into the rock, packing them with explosives, and then detonating the explosives to break up the rock and release the minerals. Before any blasting can take place, careful planning and preparation must occur to ensure the safety of workers and surrounding structures. This includes evaluating the geology of the area, designing the blast pattern, and implementing appropriate safety measures such as ventilation and blast barriers. During the blasting process, shock waves and debris are released, creating a hazardous environment for workers. Therefore, strict safety protocols must be followed, including the use of protective gear, proper ventilation, and restricting access to the blast site. Once the blasting is complete, the broken rock is removed from the mine and transported to a processing plant where the valuable minerals or ores are extracted. The Komatsu continuous miner is a type of mining equipment used to extract coal and other minerals from underground mines. It is designed to cut through coal seams of varying thickness and hardness, using a rotating drum with cutting bits to break up the rock and collect it onto a conveyor belt. The continuous miner can operate in confined spaces and is highly efficient, able to extract up to 12 tons of coal per minute. It is also equipped with safety features such as roof bolters and water sprays to reduce the risk of accidents and improve worker safety. The construction of bridges has seen significant advancements over the centuries, with various techniques and methodologies being developed to address the challenges posed by different terrains, spans, and environmental conditions. Among these innovative techniques is the incremental launching method, ILM, which has become a popular choice for building bridges, particularly those that span large distances or difficult to access locations. This method involves the construction of the bridge deck in sections, which are then pushed or launched into their final position. This essay explores the process, advantages, challenges, and applications of the incremental launching method in bridge construction. Process of incremental launching. The incremental launching method is a meticulous and systematic process that involves several key steps. Construction of the launching abutment and pier. The process begins with the construction of a launching abutment, typically at one end of the bridge site, and the necessary piers along the span of the bridge. These structures provide the foundation and support for the launching operations. Segment fabrication. The bridge deck is constructed in sections, usually ranging from 15 to 30 meters in length. These sections, known as segments, are typically fabricated in a casting yard located behind the abutment. The casting yard is equipped with all necessary facilities for producing high-quality segments. Launching process. Once a segment is completed, it is connected to the previously launched section. Hydraulic jacks or other mechanical systems then push or pull the new segment into position. This process is repeated for each segment, gradually extending the bridge deck over the piers until the entire span is covered. Alignment and finalization. After all segments have been launched, they are carefully aligned and adjusted to ensure the bridge deck is straight and level. Final finishing touches, such as the installation of expansion joints, bearings, and other components, are then completed. Advantages of the incremental launching method. The incremental launching method offers several advantages that make it an attractive choice for modern bridge construction. Minimized environmental impact. Since the majority of construction activities take place at the casting yard, the impact on the surrounding environment, including waterways and protected areas, is significantly reduced. This is particularly beneficial in ecologically sensitive areas. Improved safety. By limiting on-site construction activities, the ILM reduces the risk of accidents and improves overall safety for workers. The controlled environment of the casting yard also contributes to safer working conditions. Cost effectiveness. The repetitive nature of the ILM allows for efficient use of resources and materials. The standardized segments can be produced quickly and with high precision, leading to cost savings in terms of labor and materials. Quality control. The controlled conditions of the casting yard facilitate stringent quality control measures. Each segment can be thoroughly inspected and tested before being launched, ensuring the highest standards of construction. Adaptability to challenging sites. The ILM is particularly well suited for sites with difficult access, such as deep valleys, rivers, and urban areas. It eliminates the need for extensive scaffolding and temporary supports, which can be challenging and expensive to install in such locations. Challenges of the incremental launching method. Despite its many advantages, the incremental launching method also presents several challenges. Technical complexity. The ILM requires precise engineering and planning. The design and construction of the launching system, as well as the alignment and connection of segments, demand high levels of expertise and technical knowledge. Initial investment. The setup of the casting yard, hydraulic jacks, and other launching equipment involves a significant initial investment. While the overall costs may be reduced over the course of the project, the upfront expenditure can be substantial. Segment weight and handling. The segments, especially for large bridges, can be extremely heavy and cumbersome to handle. Proper lifting and launching equipment are essential to ensure smooth operations and prevent damage. Geometric constraints. The ILM is best suited for straight or gently curved bridges. Sharp curves or complex geometries can pose difficulties in the launching process and may require additional measures to accommodate the design. Applications of incremental launching method. The incremental launching method is widely used in the construction of various types of bridges, including highway overpasses. The ILM is ideal for highway overpasses where minimizing traffic disruption is crucial. The segments can be launched over active roads with minimal interference. Railway bridges. The method is also suitable for railway bridges, offering the advantage of constructing long spans with minimal impact on existing rail operations. River crossings. For bridges crossing wide rivers or estuaries, the ILM reduces the need for extensive in-water construction, thereby protecting aquatic ecosystems. Urban bridges. In densely populated urban areas, the ILM minimizes the footprint of construction activities, reducing noise, dust, and disruption to local communities. In modern bridge construction, launching gantries play a pivotal role by enabling efficient, safe, and cost-effective erection of bridge segments. These massive machines, also known as bridge builders, streamline the construction process, particularly for segmental bridge construction over difficult terrains such as rivers, valleys, and urban areas where traditional methods would be challenging or disruptive. Efficiency and speed. Launching gantries significantly enhance construction efficiency and speed. Traditional bridge construction methods often involve complex scaffolding and falsework, which can be time-consuming and labor-intensive. In contrast, a launching gantry can position precast bridge segments quickly and accurately. For example, in the construction of the Nanning Bridge in China, a launching gantry facilitated the erection of segments at an average rate of one span every 3 days. This rapid pace minimizes the overall project duration and reduces costs related to labor and equipment rental. Precision and safety. One of the primary advantages of using launching gantries is the precision they offer. These machines are designed with advanced computer controls and hydraulic systems that ensure each segment is placed with millimeter accuracy. This precision is crucial for maintaining the structural integrity and alignment of the bridge. In the construction of the Izhe Suspension Bridge in China, which spans 1,176 meters with a height of 336 meters above the Dahong Canyon, the use of a launching gantry was instrumental in achieving the required precision, thereby enhancing safety and stability. Cost effectiveness. Despite the high initial investment, launching gantries are cost-effective over the life of a large-scale project. They reduce the need for extensive scaffolding and minimize the impact on the surrounding environment, which can lead to significant cost savings. For instance, the construction of the Hong Kong-Zhuhai-Macau Bridge, a 55-kilometer bridge tunnel system, utilized multiple launching gantries to manage different segments of the project. This approach not only reduced construction time but also kept the project within budget by minimizing the need for temporary works and reducing labor costs. Adaptability. Modern launching gantries are highly adaptable and can be configured for different bridge designs, including cantilever, arch, and cable-stayed bridges. They can handle varying segment weights, typically ranging from 50 to 200 tons, and span lengths from 30 to 50 meters. For example, the second Penang Bridge in Malaysia, a 24-kilometer structure, utilized launching gantries capable of handling segments up to 180 tons, demonstrating their versatility and capability to meet diverse engineering requirements. Masonry has been a cornerstone of construction for millennia, traditionally involving materials such as stone, brick, and concrete blocks. However, the advent of foam blocks, specifically autoclaved aerated concrete (AAC), and foam concrete blocks, has revolutionized the field. These lightweight, durable, and energy-efficient blocks offer numerous advantages over conventional materials, making them increasingly popular in both residential and commercial construction. Foam blocks provide several key benefits. One of the most significant advantages is their lightweight nature. Foam blocks are much lighter than traditional bricks or concrete blocks, making them easier to handle and reducing the physical strain on workers. This also lowers transportation costs and facilitates faster construction. Moreover, foam blocks have excellent thermal insulation properties, significantly reducing the need for additional insulation. This makes buildings more energy efficient, leading to lower heating and cooling costs over the lifespan of the structure. Another significant benefit of foam blocks is their superior sound insulation, which creates quieter indoor environments, particularly beneficial in urban areas. Additionally, foam blocks are highly fire resistant, providing an added layer of safety. They do not emit toxic fumes when exposed to fire, unlike some traditional materials. The installation process for foam blocks is also straightforward and quick, translating to reduced labor costs and shorter construction times. The process of constructing masonry with foam blocks is streamlined and efficient. It begins with preparing the foundation and ensuring it is level, a crucial step for the stability and longevity of the structure. Traditional methods of applying mortar can be time-consuming and inconsistent. However, with a semi-automatic machine, this process is simplified. The mortar is loaded into the device, which is then moved along the row of foam blocks. The machine evenly distributes a thin layer of mortar on the face of each block, ensuring uniform application and minimizing waste. Once the mortar is applied, the foam blocks are placed on top. Due to their lightweight nature, this step is quick and easy. The blocks are aligned and tapped into place, ensuring a snug fit and a level surface. This process is repeated for each row of blocks. The efficiency of the semi-automatic machine allows for rapid progression, enabling the completion of large sections of wall in a relatively short period. The advent of semi-automatic device specifically designed for the laying of gas and foam blocks has further revolutionized the construction process. These devices streamline the application of mortar and the placement of blocks, enhancing both speed and accuracy. The first step with a semi-automatic device involves loading the mortar into the device. The device is designed to hold a sufficient amount of mortar to cover a considerable length of blocks, reducing the need for frequent refilling. Once the mortar is in the device, it is moved along the row of foam blocks. The device evenly distributes the mortar across the top face of each block, ensuring a consistent layer. This uniformity is crucial for maintaining the structural integrity and aesthetic appeal of the wall. After the mortar is applied, the next foam block is immediately placed on top. The precision of the mortar application ensures that the block sits perfectly, with minimal adjustment required. This not only speeds up the construction process but also reduces the risk of errors. The use of semi-automatic devices significantly increases the speed of construction. Workers can lay blocks much faster than with traditional methods, and the consistency provided by the machine reduces the need for rework. This efficiency translates to significant time and cost savings on construction projects. One of the primary benefits is the consistency in mortar application. Traditional methods can result in uneven layers, leading to weak spots and potential structural issues. The device ensures that each block receives the same amount of mortar, enhancing the overall strength of the wall. Reduced labor costs are another advantage. With the device handling much of the mortar application, less manual labor is required, reducing labor costs and allowing workers to focus on other aspects of the construction process. The construction process is significantly faster when using a semi-automatic device. This speed is particularly beneficial in large-scale projects where time is a critical factor. The devices are designed to be user-friendly, requiring minimal training for operators. This ease of use ensures that even workers with limited experience can achieve high-quality results. Additionally, the precise application of mortar reduces waste, making the construction process more environmentally friendly and cost-effective. The X1100RH is a highly efficient self-loading concrete mixer, designed to streamline the process of mixing and delivering concrete. It can load cement, stone, and sand automatically using its rigid 150-liter bucket with hydraulic opening, optimizing the dosing of materials. The mixer has a capacity of 1.1 cubic meters per load and can mix the materials in just a few minutes, significantly reducing operational costs and eliminating lorry waiting times. The machine features self-loading arms and a robust hydraulic system. It can elevate the mixed concrete to a height of 1070 m using a fixed gutter with a 170 degrees arc rotation and a reach of 1.1 meters for precise positioning. Powered by an Isuzu 4LE2 Tier 2 engine, it boasts a liquid 4x4 drive system with a 2-speed hydrostatic transmission and electric gear inverter. The X1100RH is equipped with a rigid front drive axle and an oscillating rear steering axle for superior maneuverability. The operator enjoys an advanced position with 180 degrees visibility, ergonomic seating, and comprehensive control over loading, mixing, and unloading processes. The machine also includes a semi-closed cabin, safety features like an audible reverse warning, and an anti-vandalic system. Additionally, it has a homologate lighting system for enhanced visibility and safety during operation. In a pioneering move for Turkey's infrastructure, БУДУЄМО spearheaded the implementation of hot tap operations, revolutionizing tasks such as insert valve installation, branching, repairs, maintenance, equipment retrofitting, and new equipment installation, all while ensuring continuous water supply on potable water lines. The essence of the hot tap operation lies in its utilization of specialized fittings which allow fluid flow to be maintained without interruption. This innovative approach guarantees the seamless functioning of a working line, facilitating line displacement or blinding, and enabling localized repairs without the need for line shutdown. While hot tap applications have traditionally found their place in the natural gas transmission and distribution sector, our adaptation for potable water systems, without compromising water supply, represents a groundbreaking advancement pioneered by this team, setting a new standard in Turkey's infrastructure development. These operations, carefully executed without disrupting water flow, are specifically tailored for steel pipes with diameters of up to 1,000 millimeters, effectively addressing the diverse needs of water administration such as ISKI and ASKI. The company proudly stands as the trailblazing institution in Turkey, having introduced the hot tap method for various diameter and property operations on potable water transmission and distribution lines. Additionally, our application extends to pipelines transporting high-temperature fluids, 185 to 200 degrees Celsius, in geothermal energy plants, marking another significant milestone in our journey of innovation and progress. Critical considerations for hot tap excellence. The success of hot tap operations hinges on meticulous planning and execution. Each operation demands the selection of the most suitable method, with unwavering attention to occupational health, safety, and environmental (OHS&E) regulations and operational procedures. Certified welders specializing in hot tap, live line welding are entrusted with the crucial task of ensuring the integrity of welding operations. Similarly, installation and dismantling tasks are meticulously handled by personnel rigorously trained in this specialized field. Prior to commencement, comprehensive measurements, tests, and checks are conducted to verify compliance with project specifications, ensuring seamless execution and minimizing risks. Pipeline installation was a critical phase of the Arsinoe-Wilson and Cole record-breaking direct pipe project, involving the precise placement of the 48 inches steel casing pipe and the 30 inches HDPE carrier pipe over the entire 3,500-foot length of the project. Here's a more detailed breakdown of the pipeline installation process. The launch pit, which serves as the starting point for the drilling operation, was excavated and reinforced. Specialized equipment, including the directional micro-tunneling machine and hydraulic pipe thruster, was brought in and set up at the site. The drilling process began with the directional micro-tunneling machine excavating the borehole under the guidance of operators at the control center. Bentonite lubricant was used as a drilling fluid to facilitate soil removal and reduce friction during drilling operations. The excavated material, along with the lubricant, was transported through slurry lines inside the pipeline being installed and pumped back to a separation plant for processing. Before installation, the 48 inches steel casing pipe and the 30 inches HDPE carrier pipe were prepared in sections. The steel casing pipe, which provides structural support and protection for the carrier pipe, was typically fabricated in lengths suitable for handling and transport to the construction site. The HDPE carrier pipe, which serves as the conduit for transporting water, was also prepared in sections, typically fused together to form continuous strings of pipe. The sections of steel casing pipe and HDPE carrier pipe were transported to the construction site and laid out adjacent to the launch pit. The sections of HDPE carrier pipe were fused together using specialized welding equipment to create continuous strings of pipe. Similarly, any additional sections of steel casing pipe needed to cover the entire length of the borehole were welded together to form a continuous casing string. A pullback string, consisting of the HDPE carrier pipe, was prepared for installation. This involved attaching pulling heads or swivels to the ends of the carrier pipe strings, which would facilitate the pulling of the pipe through the borehole from the reception pit. With the borehole completed, the pullback string was inserted into the launch pit and guided into the borehole. Careful attention was paid to ensure that the pullback string remained properly aligned and positioned within the borehole as it was fed through. As the pullback string advanced through the borehole, a hydraulic pipe thruster located in the launch pit exerted controlled force to push the string forward. This process required precise coordination and monitoring to maintain the desired speed and pressure, ensuring smooth and continuous advancement of the pullback string. Once the pullback string reached the reception pit on the opposite end of the borehole, it was carefully guided out and secured. The completion of the pullback marked the successful installation of the HDPE carrier pipe within the steel casing pipe. Throughout the pullback operation, engineers and operators monitored various parameters such as tension, speed, and alignment to ensure the integrity and safety of the installation. Any deviations or issues were promptly addressed through adjustments to the hydraulic thruster or other control mechanisms. Following installation, the pipeline underwent thorough inspection and testing to verify its integrity and compliance with design specifications. This involved conducting pressure tests, visual inspections, and other quality assurance measures to ensure that the pipeline was ready for service. Laying a double line of the EU-GAL gas pipeline is a monumental undertaking that demands significant effort from all involved parties. What makes this project truly remarkable is the scale of its dimensions. Spanning a total of 480 kilometers and traversing 3 federal states, it presents a multitude of challenges. One of the primary tasks involved in such a project is assessing its impact on the natural environment. This includes evaluating the soil, water, air, flora, and fauna along the proposed route to understand how the pipeline will affect the ecosystems. Gathering this information is crucial for determining the project's footprint and planning mitigative measures. The logistical aspects of the project are equally impressive. Coordinating the construction activities, procurement, and transportation of materials over such vast distances requires meticulous planning and execution. With thousands of meters of pipeline and tens of thousands of welds involved, managing the logistics becomes akin to juggling multiple tasks simultaneously. The preparations for the realization of the EU-GAL pipeline took approximately 3 years. It traverses 3 federal states, beginning in Lubmin and extending through Mecklenburg-Vorpommern, Brandenburg, and finally reaching Saxony before connecting to the NET4 GAS system at Deutschneudorf on the Czech border. Despite the vast scope of the project, there was a tight timeline of just 2.5 years for construction. This timeframe encompassed various tasks such as land use planning, permitting procedures, and execution across multiple jurisdictions. One significant aspect of the project was engaging with landowners and communities along the pipeline route. With over 7,000 parcels of land affected, negotiations and agreements with property owners were crucial. Building credibility and fostering public acceptance were essential components of this process. Finding an acceptable route for the pipeline involved extensive planning and environmental assessments. Identifying suitable locations while considering factors such as biodiversity, soil composition, and protected areas was a complex endeavor. Measures such as visual screening of construction activities near sensitive habitats were implemented to minimize ecological disturbances. The construction phase involved the installation of thousands of pipes, each weighing approximately 15 tons and spanning an average length of 18 meters. Innovative approaches such as micro-tunneling were employed to navigate challenging terrain features like rivers and protected areas. In addition to the physical construction, the project included the installation of gas pressure regulation and measurement stations. These facilities play a critical role in ensuring the efficient operation and management of the pipeline network. The completion of the EUGAL pipeline represents a significant milestone in Europe's energy infrastructure. It not only strengthens the continent's gas supply network but also demonstrates the successful collaboration between diverse stakeholders, including government agencies, private companies, and local communities. Looking ahead, projects of such magnitude may become increasingly rare. However, the lessons learned from the EUGAL pipeline construction will undoubtedly inform future endeavors in energy infrastructure development, paving the way for more sustainable and efficient solutions. Installing and operating a boring machine, such as the American Augur's Quick Tran system, involves a series of meticulous steps to ensure both efficiency and safety throughout the process. From the initial installation to the operational procedures, each stage demands attention to detail and adherence to specific guidelines. The installation process begins with thorough preparation, ensuring all necessary components are readily available and inspected for any signs of damage or wear. This includes casing adapters, master saddles, and other essential parts. Fluid levels must be checked, and operational tests should be conducted to verify the machine's functionality before proceeding further. In the case of split design machines, a distinct set of assembly instructions must be followed. These machines feature two sets of lift points, each serving a specific purpose. Care must be taken to utilize the correct lift points and spreader bars to maintain stability and prevent any mishaps during assembly. Aligning keys on the base with notches in the master track is crucial, and precise measurements should be taken to ensure equal distances from corners to the gear racks inside. Engaging the quick tran mechanism is a critical step in the installation process, particularly for machines equipped with this feature. The mechanism must be in the open position during insertion to prevent any potential damage. Once aligned with the gear rack, the bolts securing the mechanism must be torqued to the specified values based on the machine's configuration, ensuring a secure attachment. Completing the assembly involves installing the power package into the base unit and making necessary hydraulic and electrical connections. Care must be taken to clamp swivel bolts securely, ensuring that all connections are properly latched and tightened to prevent any potential leaks or malfunctions during operation. Moving on to operational procedures, a thorough pre-start check is essential to verify the machine's readiness for operation. This includes checking engine oil and fuel levels, ensuring the air filter is clean and functional, and closing the spoil chamber door. Setting the transmission to neutral and pulling the emergency stop switch up further prepares the machine for startup. Starting the engine involves turning the ignition key to the run position and adjusting the throttle to half speed for engine warm-up. Once warmed up, the push bar is engaged with the track, and the quick tran function is activated to align the motors with the track. Retaining pins are inserted to ensure proper engagement before starting machine operations. Operating the quick tran function requires careful attention to detail, as it facilitates both forward, thrust, and backward, retract, movements. A lever located away from the thrust lever controls this function, and operators must ensure all connections are secure before use. Before activating quick tran, the push bar must be disengaged from the track to prevent any interference with the machine's movement. Shutting down the machine involves allowing the engine to idle for cooling after operating under load. The emergency stop switch is pushed in, the ignition key is turned to the off position, and the key is removed for security purposes. By following these detailed procedures, operators can ensure the safe and efficient operation of boring machines, maximizing productivity while prioritizing safety at every step. First, clean pipe roughly. Then mark the area which must be peeled. Peel the pipe in this area. Clean the fusion zone with Tangent PE cleaner. Afterwards, let the cleaning agent evaporate. Unpack the LGIF plus tapping saddle without touching the fusion zone. Mount the tapping saddle and tighten the screws. Mark the saddle position. And align the outlet as desired. You can additionally start the fusion process with the start-stop code. Start the fusion and supervise the process. Check the fusion indicator and the saddle position. Mark the fusion. Determine area which must be peeled. Mark the area which must be peeled. Peel the pipe. And clean the fusion zone with Tangent PE cleaner. Determine and mark the insertion depth. Unpack the coupler without touching the fusion zone. Mount the coupler and ball valve. Ensure fusion area remains stress-free. If there is the risk of stress or dislocation, use a clamping tool. Scan the fusion parameters and traceability data. Start the fusion and supervise the process. Check the fusion indicators and mark the fusion. Wait until the cooling time is completed. First, close the ball valve. And then tap the main pipe. Turn back the cutter up to the upper stop. Check for the presence of the cut-out PE pipe section in the cutter base. Tighten the screw cap by hand. Mark the tapping. Mount the extension spindle. Hydraulic fracturing produces fractures in the rock formation that stimulate the flow of natural gas or oil, increasing the volumes that can be recovered. Wells may be drilled vertically hundreds to thousands of feet below the land surface and may include horizontal or directional sections extending thousands of feet. Fractures are created by pumping large quantities of fluids at high pressure down a wellbore and into the target rock formation. Hydraulic fracturing fluid commonly consists of water, proppant, and chemical additives that open and enlarge fractures within the rock formation. These fractures can extend several hundred feet away from the wellbore. The proppants, sand, ceramic pellets, or other small incompressible particles hold open the newly created fractures. Once the injection process is completed, the internal pressure of the rock formation causes fluid to return to the surface through the wellbore. This fluid is known as both flowback and produced water, and may contain the injected chemicals plus naturally occurring materials such as brines, metals, radionuclides, and hydrocarbons. The flowback and produced water is typically stored on site in tanks or pits before treatment, disposal, or recycling. In many cases, it is injected underground for disposal. In areas where that is not an option, it may be treated and reused or processed by a wastewater treatment facility and then discharged to surface water. The ballast bed is the layer of crushed stone that supports the railway track and helps to distribute the weight of the trains evenly. The lorem ballast cleaner works by excavating the ballast bed, lifting the ballast onto a conveyor system, and then sieving out the fines and debris from the ballast. The clean ballast is then returned to the track bed, while the fines and debris are deposited in a separate hopper for disposal. The machine is equipped with a series of screens and magnets that separate the ballast from the debris, including dirt, rocks, and vegetation. The screens are adjustable, allowing the operator to control the size of the ballast that is returned to the trackbed. The Lorem ballast cleaner is designed to improve the stability and drainage of the railway track by removing fouled ballast and allowing fresh ballast to be added to the trackbed. This helps to prevent derailments and other track-related issues.